And we are live. Welcome to Math with Doug. Today it's going to be multiplication with Doug, specifically the multiplication table with Doug. And Mocha is here, that's the dog, but she's not going to be very much help at all. She has a dog dish that's designed to be kind of a puzzle that has 6 little places where I put her food, and there are covers that cover those, and she can slide them with her paw and find the food. And very often, when I take the empty dish to give her her next meal, I discover that one of the 6 little containers still has food in it, which means either her nose doesn't work very well for her not to know it's there. It might mean she can't count. I think she can't count. But multiplication is like counting. You learn to count first, and then you learn to multiply. And already knowing how to count really helps you to learn to multiply. It could be that she just isn't hungry enough to eat all 6 of the little containers of food, and she might have me completely outsmarted. But all that aside, I am going to put the dog aside, and we are going to get into this multiplication table, which is empty. I admit it, it's empty, but I'm going to fill it. Okay, down you go. Lie down. Lie down. Stay. Stay for an hour. We'll see if she can do that. Okay, so I'm wearing my Holland soccer jersey, sort of a national team jersey. I don't think it's really the official one, but it's nice, it's comfortable. And it's cold outside, and the winter is lasting too long, so I don't really want to think about the weather. In fact, I have the blind pulled over there in that window, and I'm happy I don't have to see the neighbor's snow. Let's get into the multiplication table. Okay, so I didn't even put the numbers along the side and the top, because I thought I should actually do that as part of the lesson. And I decided to try something. I hope I don't regret it, which is I'm going to use colored chalk. I'm going to try to use, this is yellow, I'm going to try to use colored chalk to our advantage. Because the thing about this table, when it's all filled in, is it sort of tricks students who are trying to learn the multiplication table into thinking that it's more work than it really is. It actually isn't that bad, but sure, that's a lot of little squares that I'm going to fill with numbers, so it seems like a lot of work. But I'm going to try to use color to show some of the patterns that make it easier for us to learn the multiplication tables. Why do we do this? Why do we want to memorize the answers to a whole bunch of multiplications involving small numbers? Because it saves us time later when we're working on other types of math, when we are doing a multiple step problem, an interesting thing that we're just learning how to do, and some of the steps involve multiplication. Instead of having to stop and try to figure out the answer to a multiplication, if we've memorized a lot of the more commonly used ones, we're able to quickly put the answer to that multiplication into its place and then just continue with what we were doing and stay focused on what we're actually trying to learn. So that is very helpful. And having multiplication tables memorized saves us time. So the first thing I'm going to do is I'm going to put the numbers 1 to 12 along the top and down the side. I'm not showing the zeros. They can be shown, some tables will have them. And some tables only go up to 10 times 10 and don't show the 11s and the 12s, but I want to show the 11s and the 12s. So that's the way I'm doing it. Now, the very first thing I'm going to say though, before I even start writing in any numbers, is for a student who wants to work on this, having an empty multiplication table is very useful. And they're easy to find. You don't really have to draw it. I drew this one. And I'm telling you right now, I do not want to have to erase this and draw another one during this lesson. So I'm going to try not to get too messy, because it took me 20 minutes to draw this so nicely on a chalkboard wall. So the students shouldn't be spending too much time trying to draw all sorts of lines and make a nice neat table. Ideally, you find an empty multiplication table and that you can make as many copies of as you need. And then the first thing that I want the student to do, once they have some empty ones to work with, is I want the student to write in the numbers 1 through 12 on the side and on the top in that student's own handwriting. So I'll do it now in my handwriting, and I'm using the yellow. So this is 1, and then I am basically, what am I doing right now? I'm counting. And we all know how to count. We wouldn't be learning the multiplication tables if we didn't already know how to count. So we just have to be able to count to 12, and that's not the most difficult assignment. So that's what I'm doing right now, but I'm doing it while filling in the numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that's a messy 9, but I'm going to keep it 10, 11, and 12. When you get to the 2-digit numbers, it gets to be a little bit more difficult to fit them into these little squares, but we're just going to have to manage. Fortunately, there are not too many 2-digit numbers or 3-digit numbers involved in the multiplication table, so I'm just going to have to write those a little smaller. Okay, so I put those kind of on the outside of the table, if you can see that. I didn't really complete the squares that those numbers are in, and now I'm doing the same thing over here in these incomplete squares. 1, 2, what am I doing? I'm counting. 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. There. Okay, I counted. And I keep on mentioning that I'm counting because counting is a useful skill when you are filling in the multiplication table. Because I think the students who are watching know how to count the way I just did, but they also know how some other tricks, like how to count up by 2s or even by 10s, things like that. And that type of skill comes in handy when we do this exercise. So I used the yellow just for the heading numbers and the, I don't know what you call the ones on this side, the numbers on the left side and the top of my multiplication table, they're all in yellow. I'm going to put most of the answers being the answer you get when you multiply 2 numbers, in white. And I'm going to try to use some other colors to highlight certain parts of the table so that we can appreciate patterns. Patterns are important when you are doing the multiplication table. So now I'm switching to white. Now, let's see, how am I doing for time? I've already used 7 minutes just with this sort of intro. I haven't even started filling in the table yet. What I want to urge the students to do is once you have a multiplication table where you, with your own neat handwriting, have put in the numbers 1 to 12 and 1 to 12, make a copy of that so that you can print multiple copies of that if you need it. And then you have a bunch of blank tables that already show these headings that you can fill in yourself. And what happens is, at certain times along this process that we're doing, as we start filling in this table, we can keep on recording what the table looks like at that moment when we filled in parts of it but not done others yet. And if we want, we can save that and make copies of it. So if you're working on, say, the squares, which is the numbers that go in the diagonal of the table, if you've learned a lot of it and you're still working on those, what you can do is you can use a copy of the table where a lot of the more easy ones that you've already learned are already filled in your own handwriting, ideally. And then you just have some blank spaces that include the ones that you're still working on at that moment. The reason for this is because it seems like too much. Right now, it already seems like too much. Even though I filled in these numbers in the top and the side, it seems like too much. This is too much work. This is what the student might be thinking. What, they expect me to know all of that? I'm supposed to fill in this whole thing? I'm supposed to know all these answers to multiplication? You don't work on the entire table at once. There will be parts that you find easy that you'll work on first and get really good at first, and then you'll move on to other parts of the table. So it's not all at once. Okay, let's do the ones, because we're not going to really find much surprises when we do the ones. Because the ones are, what I mean by the ones are all the answers that go right here, but also all the answers that go right there. So whenever I do 1 times 1, 1 times 2, or 1 times 5, 1 times 8, I'm multiplying by 1. And of course, when you multiply by 1, the answer is the number that you multiplied by 1. So 1 times 1 equals 1. There, I have an answer. It's in white. 1 times 2 equals 2. And we realize, if we stop and think about it, that it feels like we're doing something we already did. We already filled in this thing on the top by counting. We were counting up by ones, And now we're doing that again. 1 times 3 is equal to 3. 1 times 4 is equal to 4. And you might be saying, well, I kind of already know this. I already know how to count. I kind of proved it already when I did this. So I'm just doing that again. I'm counting. I'm counting up to 12 again. And that's not hard. So the student might be forgiven to want to just go faster and just count by ones. 1, 2, 3, 4, 5, 6, 7, 8. But I urge you instead to be saying 1 times 5 equals 5. It still is just as easy, but you say a few more words. 1 times 6 equals 6. 1 times 7 equals 7. So I am counting by ones. But I'm doing it in a different way where I'm saying each of those multiplications and the answer. And it ends up giving me the same knowledge that I had when I was counting up by ones. 1 times 8 equals 8. 1 times 9 equals 9. 1 times 10 equals 10. 1 times 11 equals 11. 1 times 12 equals 12. Okay, the ones are not that much trouble. And look, we already filled in that whole line with the white letters here. That's 12 answers. But wait, is it only 12 answers? Because this is also the ones. But now, instead of saying 1 times 1 equals 1, I'm saying 1 times 1 equals 1. Does it look like I just said the same thing twice? I guess it does, especially when we're in this top corner. But that one's already filled in too. Wow, that's funny. Trying to do this row, I already have the first answer there. This is one of the things that I want to point out to students that show the students, okay, it looks like it's going to be a lot of work, but it actually keeps on not being quite as much work as we thought, which hopefully makes us feel better about it and makes us feel smarter. I like feeling smart. Okay, 1 times 2, well, no, am I saying that right? 1 times 2 equals 2. 2 times 1 equals 2. Well, it is the same answer. 1 times 2 equals 2 times 1. I'm going to write that over here. 1 times 2 equals 2 times 1. That's interesting. What's a 2? Let's think. What's something that's a 2? Something that comes in 2s. I'm looking for something that I can just grab, but I don't know if I'm going to find anything. So let's say I draw something like this. It's like a rectangle that's cut into 2 equal-sized squares. Okay, so that's one of these, and it includes 2. It's one rectangle that includes 2 squares. But I could do it like this instead. Is that helping? I don't know if that's helping. Okay, so I could say that's 1 times 2, or it's 2 times 1. Yeah, in a way this sort of illustrates what I'm showing here. The point is, 1 times 2 is the same as 2 times 1. I don't know if 1 times 2 is the best pair of numbers to illustrate that with, so I'm going to do it again when we get to some slightly larger numbers. Okay, and then of course, what does this mean? This is 3 times 1. You might say, hey, we already did 1 times 3, so that's just 1 times 3 again. But I'm going to say it's 3 times 1, and that is equal to 3. 4 times 1 is equal to 4. So it's almost the same thing, but it's not the same thing. We did 1 times 1, 1 times 2, 1 times 3, 1 times 4, 1 times 5, all the way up to 1 times 12, and now we're going 1 times 1, 2 times 1, 3 times 1, 4 times 1, 5 times 1, all the way down to 12 times 1. And yes, we are getting the same bunch of answers. 5 times 1 is 5, 6 times 1 is 6, 7 times 1 is 7. Maybe I'm speaking too quickly. 8 times 1 is equal to 8. 9 times 1 is equal to 9. 10 times 1 is equal to 10. 11 times 1 is equal to 11. And 12 times 1 is equal to 12. And there we go. With one set of knowledge that we already proved we understood here, we just took all of that same bit of knowledge, that understanding, and we filled in this section too. We have now filled in this whole line across and this whole line down, all just by multiplying by 1, or 1 being multiplied by something else, or counting by ones, which is the way we're used to counting. We can count other ways, but the way we count the most often is increasing by ones. Let's move on and do the 2s. I think it's time for the 2s. I'm looking how much time I've used. I'd really like to get to filling this whole table by the end of 1 hour. We'll see if I can do that. I might have to go more quickly through some of these sections and then slow down in others. But it's always good to not try to start too quickly. So even though multiplying by 1 is not very difficult, and I have a feeling most of the students who are watching already know how to do it, it's still the beginning of this lesson. It's still the introduction to the concepts of the lesson, so it should not be rushed, so I don't want to rush it. I am going to erase this little thing, and I'm going to try to do this again, but with different numbers. I think it works better with different numbers. Sometimes ones are too easy. Okay, 2's. What do you do when you multiply by 2? Again, I would say going across, I read that as 2 times 2 equals, and I think the students might know that 2 times 2 is equal to 4. But let's slow down. 2 times 2, well, if you have 2, but then you do it again, it means you have this 2, but you have it 2 times. And this 2 times, if we count how many of these we have, well, there's 4. So it's kind of like counting. It's kind of like adding, isn't it? 2 plus 2 is equal to 4, but 2 times 2 is also equal to 4, and that's illustrated here as well. 2 plus 2 equals 4. We can see that there are 4 of them there. If we can count 1, 2, 3, 4, yes. But 2 times 2, 2 times, it's nice to slow down and think about the words you're saying and their meaning. So again, how did I say this again? I said 1 times 1, 1 times 2, 1 times 3, then 2 times 1, 3 times 1. Yeah, that's the way I want to do it. So the one on the left is the number I say first, then I say the word times, and then I say the number that's on the top. I'm going to try to keep on doing it that way so that I don't go backwards and forwards and get confusing. Okay, so 2 times 2 equals 4, and 2 times 3 equals 6. 2, there's something that's a 2. We can see there are 2 of these little circles, whatever that is. I don't know, maybe it's Mocha's nose or something. But I don't think I did a good job of drawing her nose. So what I'm going to do is erase all of these little Mocha noses or whatever they are. I'm going to just say, I'm not going to try to say what it is I'm drawing. I'm just going to say it's 2 circles that are right next to each other. And we can see that there are 2 circles. 2 times 3. 2, and I'll do it a second time, and a third time times 3 means the same thing. Yes. 2 times 3. Really, stop and slow down and say the words and think about what they mean, and it just sort of makes sense. 2 times 3, 1, 2, 3, 4, 5, 6 is equal to 6. What else am I doing though? Counting up by 2's. Counting up by 1 seemed like it was, I'm talking about it for no reason because everyone understands how to count, so they know that we're counting up by 1's. But counting up by 2's is something that we tend to also do. Often we have reasons to count by 2's. So 2 plus another 2 is 4, plus another 2 is 6, plus another 2 is 8. What did I just say? 2 plus another 2 plus another 2 plus another 2. I kept on saying 2. How many times did I say it? I said it 4 times. 2 times 4 equals 8. 2 times 5 equals 10. So when we do the multiplications and say them out loud, we're really doing the same thing that we do when we add. If we keep on adding 2 more. So 2, add 2 more, we get 4. Add 2 more, we get 6. Add 2 more, we get 8. Add 2 more, we get 10. Or 2 times 1 equals 2. 2 times 2 equals 4. 2 times 3 equals 6. I like that. I'm going to keep saying it because that's really what we're trying to do. We're not trying to add right now. We're trying to multiply. But we think about how we already kind of knew how to do it because we already knew how to add. 2 times 6 equals 12. 2 times 7 equals 14. 2 times 8 equals 16. 2 times 9 equals 18. 2 times 10 equals 20. 2 times 11 equals 22. 2 times 12 equals 24. I am still able to fit these 2-digit numbers into these little squares. And then we already know what's going to happen next, don't we? We keep on seeing this, learning the same lesson. This table that seemed like it was going to be so much work to fill in, every time we do something, it counts twice. Because if we can do the 2's along this way, we can do the 2's down that way. And it's really the same thing, except we say the 2 numbers we're multiplying in the opposite order. So here, I'm doing 3 times 2, not 2 times 3. 2 times 3 happened here. Now I'm doing 3 times 2, and I get 6. 4 times 2, and I get 8. So now I'm saying these numbers that are increasing by 1, and each time I say the number and I say times 2. Instead of saying 2 times, I'm saying something times, I'll say it that way. Instead of saying 2 times something, I'm saying something times 2. And I realize that this lesson that I drew before starts being easier to see with slightly larger numbers. So let's do with the very next square we're going to fill in. It's going to be 5 times 2. 5 times, that's a 5. 5 times 2 equals 10. We already knew that 2 times 5 equals 10. 2 times 5 equals 10. It's one of the really nice things about multiplication is that it doesn't matter which number you put first. 5 times 2 is the same thing as 2 times 5. 5 times 2, so I'm making these little drawings that each look like, you can see that there are two little squares put together. They kind of look like dominoes. 5 times 2, it's getting messier the lower I get down on my chalkboard wall, is equal to 2 times 5. That's not a domino. I don't know what that is. It's a lot bigger than a domino, but it's kind of like a rectangle, but it's got 5 equal sized squares in it. 5 times 2 is equal to 2 times 5. And if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. And yet again, we see examples of how knowing how to count helps us to understand how to multiply. 5 times 2 equals 10, 2 times 5 equals 10. Am I going to do this with every single pair of numbers in this table? No, because I do not have time. But I could. So when we get up to a great big number like 327 times 17,000, I don't know what the answer is going to be, but it's going to be the same as 17,000 times 327. Ha! Because we sort of learned a rule that when you multiply two numbers, it doesn't matter which number you put first. And that's reflected in the table, where when we fill in a whole line, we've just done the work that we can just do to fill in another line. And every time we fill in a chunk of this table, we fill in 2 chunks. And it means that the whole table ends up being only half as much work as it looked like it was going to be at the beginning. Let's finish this little stretch, and then I'm going to talk about printing out the table again. 5 times 2 is equal to 10. Well, I guess we know that. We really went into detail on that one. 6 times 2 is equal to 12. 7 times 2 is equal to 14. 8 times 2 is equal to 16. 9 times 2 is equal to 18. 10 times 2 is equal to 20. 11 times 2 is equal to 22. And 12 times 2 is equal to 24. And I need more chalk. There. And I need to take a sip of my fizzy water. And I will remind all of the students, when you are spending a whole hour learning math, it helps every now and then to take a sip of water. Mandarin orange flavored fizzy water. It's as if somehow the process of thinking about numbers makes us use up water in our body so that we feel thirsty and we need more water. Interesting that thinking about numbers would do that. It might also have something to do with when you're a teacher who's a big chatterbox and you talk and you talk and you talk, that also makes your body use up water. I think I might be onto something there, but that would be entering the field of science. So let's stay in the field of math and just say calculating numbers in your head uses water in your body, and you have to drink some fizzy water or some regular water every now and then just to achieve that watery balance inside of you. And also, don't forget to stretch, especially around the shoulders, especially if you just spent 20 minutes drawing a really beautiful, neat table on a chalkboard wall. Okay, so a whole bunch of this table is filled in. When we look at all the blank spaces, it's so much smaller than it was before. The amount of work that we still have left to do is so much smaller. And we start with things that we find easier, things we feel ready for. Okay, I might not be ready to do all the 9 times 7 type of things yet, but I can do these 1 timeses and I can do the 2 timeses, so I'm going to do those first. And then this thing about printing. If you get to a certain stage in your learning, you might get to a stage where you realize that you're really good at all the ones and the twos like this, and you really don't feel like you need to work on them anymore. It's like you know them, you just feel you know them. But there's still other things you want to work on. So you might want to take a table that's filled in this much and save a copy of that, and maybe print copies of it, and then you have multiple pieces of paper to use that already have the ones and twos filled in, to use while you're filling in the rest, while you're working on the next bunch of numbers. Okay. There are so many patterns that I want to talk about that happen in this table, and I'm going to use the colored chalk, but what I'm going to end up doing is waiting until the table's more full, and then erasing some of the numbers I've already put in and rewriting the answers, but in the color I want so we can see the pattern. See a pattern emerging. How am I doing for time? Not bad. What should I do next? Now, there are different orders in which we can approach these numbers. And twos was a really good one to do near the beginning. Ones is also pretty good to do near the beginning, but I don't necessarily want to do them all in order. I want us to be able to start filling in some of the other sections of the table. And I'm being so expressive right now, using my hand. I have two of these, yeah. And most of us have, you know, two hands, and we have 5 fingers on each hand, right? Let's show them all at once. Okay. The number 10 is very important in the way we do math. We use tens in special ways. Like, for instance, you notice that we have all these symbols for all the numbers, and when we get to 10, we start using 2 digits. It's 10 when we start using 2 digits. There's a reason for that. The reason is that 10 is an important number. When people first realized numbers existed and that we could use them and talk about them and do math with them, we realized 10 was important right from the beginning. And why? Why did we choose 10 as such an important number? Well, I think the answer is right there. We have 10 fingers. If you count the thumbs as fingers, and yeah, you should, they are. When you think about how many fingers you have on each hand, how many fingers you have on both hands, yes, we have 10 fingers. So 10 is useful. It was already useful before people even realized that we could do things like counting. People probably already used the 10 digits on their hands to do math with before anyone had invented the idea of counting. So tens, let's work on the tens. Ten's way over here, and it's way down there, so it feels like it's, well, no, the bottom right is the really hard part of the table. That's what you'd think. All the bigger numbers are there, and if you see a filled in, completed multiplication table, you do notice that you have bigger numbers. You even have some 3-digit numbers down there. But does that mean it has to be the hard part of the table? Well, parts of it are not going to be very hard because the tens are there, for example. That's just one example. So let's fill in another chunk of this table. The tens. I can count up by tens, and it feels very similar to counting up by ones. Let's try counting by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. Oh, I could keep going. So yes, counting up by tens isn't that hard, but we don't want to really do a counting lesson today. So we want to remind ourselves that what we're really doing is a multiplication lesson. So what do I do along here? Ignoring most of the numbers, but wanting to focus on 10, I can say 3 times 10 equals 30. And that's the same number I get if I'm counting up by tens, and I say 10 and then I say 20, the next number is 30. So 10, 20, 30, I'm counting up by tens. 3 times 10 also gives me 30. 4 times 10 gives me 40. Hey, I'm doing the down part first instead of the across part. But that's another thing that I can choose to do if I wish. I do choose to. 5 times 10 is equal to 50. I'm getting the same answers I get if I count up by tens. 6 times 10 is equal to 60. 7 times 10 is equal to 70. 8 times 10 is equal to 80. 9 times 10 is equal to 90. 10 times 10 is equal to 100. I got to my first 3-digit number already. 11 times 10 is equal to 110, which is easier to fit into that square than the 100 was. 12 times 10 is equal to 120. Now this is challenging for me. This 2 takes up a bit of space. I'll make the 0, it's kind of skinny 0, and it fits. I did it, and it's also hard for me to write that low on the chalkboard wall, and my handwriting gets messier. I don't want my handwriting getting messier when I'm getting to the longer numbers. That would be a problem. I have to slow down. Let's do the across though. 10 times 1 is equal to 10. We already had that. 10 times 2 is equal to 20. 10 times 3 is equal to 30. 10 times 4 is equal to 40. 10 times 5 is equal to 50. 10 times 6 is equal to 60. 10 times 7 is equal to 70. 10 times 8 is equal to 80. 10 times 9 is equal to 90. 10 times 10 is equal to 100, but we already had that. Now that we're not sticking to the outside of the table, we're going across the middle of the table, we start seeing the interesting thing happening there. If you manage to fill all the 10s downwards, then when you're going across, you get to one that's already done. 10 times 11 is equal to 110, and 10 times 12 is equal to 120. At what point should I start using colored chalk? Should I have used an interesting color for the 10s? I don't know. I don't know if it's necessary because they were kind of easy. I think the students find them kind of easy, the 10s, so maybe we shouldn't be going for a special color just for that. And I also know that these colored chalks are only so useful when you're teaching with a video or with a Zoom meeting, because it's harder for the colors to show up. Do the students who are watching this even see the difference between these yellow numbers and these otherwise identical white numbers that are right next to them? When I look at the video from here, I'm kind of far away. I'm going to try and look. Get out of the way, Doug. See, I can see that it's yellow and white, but it's not a very big difference between the yellow and the white. So that's a problem, because yellow would be such a useful color to use otherwise. And then when we look at the other colors, the darker colors, like this blue, are harder to see on a video. They look great when you're standing right near the chalkboard like this. Colored chalk is great, but for videos, not so useful. And now we look at how much is left to do. And again, a student who's really good at the 1s and the 2s and the 10s might want to save a copy of their multiplication table filled in this much so that they can use that while they're working on the next numbers that they still are finding there might still be a bit of a challenge. And that's helpful, because then you can focus on the numbers you're working on. And it is getting to seem like less and less work. And I look at how much time is left, I'm not feeling quite so worried. It feels like we've already filled in almost half the table. Have we? There's 12 of them, 12, 24, 36, but then there's overlap. I have to be careful when I count these. Plus another 45. I think I've done 63 of the numbers. How many numbers are there? There are 144 numbers altogether. There, 112. There are 144. Hey, I just kind of showed off that I know that 12 times 12 is equal to 144. Didn't mean to jump so far ahead in the multiplication table. Should I write in 144 right now? No, I'm going to talk about it some more. But yeah, 144 numbers, and we've already done 63 of them, I think. 63 is almost half of 144. We have done almost half of the table. And even though I started off slowly, I still have almost half of my planned lesson time left. I think we're going to succeed at doing this. What we need to do is pick another one that we find is the one we should work on next. And you know, it could be a matter of opinion of what's the next one we should work on. But I have a feeling that this whole theme about 10 fingers, I can sort of continue that by reminding us that, well, if you only use one hand, that's 5. So 5s might be also considered to be a nice, not so tough next number to work with. And the 5s would go down along from this 5 down here, but also across from this 5, and they'd really help fill in some of this big central area that we haven't done anything with yet. So yes, I like the idea of going up by 5s, and I think people count by 5s a lot as well. Counting by 1s, of course, everyone has to learn how to do that quite early. Counting by 2s happens a lot. There are a lot of reasons to count by 2s. There are often a lot of reasons to count up by 10s. But what about counting up by 5s? But we're not counting. We're using the fact that we already know how to count up by 5s to help us multiply by 5. So that time I went down first. This time with the 5s, I'm going across first. I'm going to do it that way. 5 times 1 is equal to 5, but we knew that, didn't we? 5 times 2 is equal to 10. 5 times 3 is equal to 15. Aha. 5 times 4 is equal to 20. I'm going to erase this. It shouldn't be here anymore because we're not doing the 2's anymore. 5 times 4 is equal to 20. Okay, 5 times 5 is equal to 25. And yes, if we just counted up by 5's instead, we'd still be able to fill it in. I don't know if we would be learning as much. 5, 10, 15, 20, 25, 30. I know 30 is next, but I want to say 5 times 6 is equal to 30. To remind myself that I don't need to work on counting up by 5's, I do need to work on multiplying by 5. 5 times 7 is equal to 35. 5 times 8 is equal to 40. 5 times 9 is equal to 45. That's one of the ones that might take a little longer for people who are just starting to do their multiplication. 5 times 9, 45. Maybe that's the first one I've gotten to in all of these questions that I might think some of the students might find that one slightly tricky. Not very, very tricky, slightly tricky. 5 times 10 we already had, that's 50. 5 times 11 is 55. 5 times 12 is 60. I think it's time for me to try something that involves adding a new color. And I don't think the 5's made it necessary. So what I'll do instead is I'll do the down part of 5's. And remember, I'm saying the numbers backwards from the way I just did. 5 times this, 5 times that, 5 times the other. Instead, I'm saying 1 times 5 is equal to 5, but we knew that 2 times 5 is equal to 10. 3 times 5 is equal to 15. 4 times 5 is equal to 20. 5 times 5 is equal to 25. That keeps happening too. We keep on hitting numbers that we don't have to write down because we had already put it in. 6 times 5 is equal to 30. 7, that's messy. 7 times 5 is equal to 35. 8 times 5 is equal to 40. There's 9 times 5, there's that one, is equal to 45. 10 times 5 is equal to 50, already there. 11 times 5 is equal to 55. 12 times 5 is equal to 60. And look how much space we have filled in this table. Which one do I want to do next? I'm going to use some color. I really feel like I want to use some color. So, how about I use green for a very special set of numbers in this table that allow us to illustrate something interesting. And it is a little bit more challenging with the multiplication, I admit that. It's what we call the squares. What are we calling them squares? We know that a square is a shape where there's 4 sides and the 4 sides are equal in length. The length is equal to the width. So what's a square and multiplying though? That's when you multiply a number by itself. Kind of interesting. So 1 times 1 is a square then. We did that already, remember? See, it's right there. 1 times 1, and that one's only happened once. All the other ones happened along there and down there, but the 1 times 1 only happened once. That's kind of interesting. 1 times 1 equals 1, and that's a square because I'm multiplying a number by itself. So because I felt like using color, I'm going to erase that answer that I put in earlier, and I'm going to put it back in, but with the green chalk. And now we can see whether the color really shows up well in the video. When I get that close to the camera, I have to take off my glasses. So 1 times 1 equals 1. Yeah, it's green. Slightly different color. 2 times 2 is also a square. 2 times 2 means 2 times itself. 2 times 2 is equal to 4. I think I need to put that in green. 2 times 2 is equal to 4. Should we jump ahead? Why not? 5 times 5 is a square and it's equal to 25. So that means this 25 that we already put in needs to be in green. Now, the students who are working on this don't have to use different colors when they're learning, when they're filling in their tables. I'm just choosing to do it because it allows us to sort of see some of the patterns. I like the pattern. 10 times 10 is a square and it's equal to 100, so I'm going to replace that one with a green 100. And before we finish all of the squares, which we will do next, and all of them will be in green, we're going to stop and look at these 4 squares that we've already done. The 1 times 1, the 2 times 2, the 5 times 5, and the 10 times 10. They have something in common. But what do they have in common besides the fact that I'm writing them in green? I don't mean that they're green. What else do they have in common? I kind of noticed it before when we did the 1, remember? 1 times 1 only happened once. 2 times 2 happened here. Where's the other one? It also only happened once. Whereas we did 2 times 3 and got 6, but we also did 3 times 2 and got 6. So when we do, I'm gonna write that off to the side. This is worth thinking about. I don't want to use the green chalk for this, so I'll go back to my white chalk. 3 times 2, which is 3 times 2, that's this 6. But there's another 6 there, which is also from 2 times 3, 2 times 3. 3 times 2 and 2 times 3 both gave us 6, but we ended up having to write the answer in 2 different spots in the table, depending on which of the 3 and the 2 we said first. But 2 times 2 only happened once. We didn't have to do it twice, because of course, if we did 2 times 2 and set it backwards, we'd say 2 times 2 again. This 2 times that 2, we write that as 2 times 2. This 2 times that 2, we also write it, so it doesn't really matter which one we put first when the 2 numbers that we're multiplying are the same number. And that's kind of interesting, because those are the ones that are only happening once in the table. That's neat. So let's do the rest of the squares. 3 times 3 is equal to 9, and I only have to do it once. 4 times 4 is equal to 16, only have to write it once. 6 times 6 is equal to 36. Now, we're getting into some of the ones that some of the students won't know yet. Because when you get into this area of the table, we get into some of the numbers that a lot of students will learn last. But I think the diagonal kind of helps. The squares help. The number multiplied by itself helps for us to conquer some of the territory in that little region of the table. 7 times 7 is equal to 49. And I think a lot of students are not going to be saying to themselves, I've heard of that, yeah, I knew that 7 times 7 is equal to 49. We're getting into some weirder looking answers. But if you counted 7 plus 7 plus 7 plus 7 plus 7 plus 7 plus 7, meaning 7 times, which is the same thing as 7 times 7, if you counted up by 7s, you would get to 49. You might have to be careful. And then 8 times 8, 64. 9 times 9, 81. These have a lot in common. They're only happening in the table once. They're green, the way I'm doing it today anyway, they're green. But they're numbers, they're multiplication answers that you might have to spend a little bit more time learning. But once you learn them, you might find them easier to remember because they're the squares, because they're on the diagonal. 10 times 10 is equal to 100, but we knew that. 11 times 11, that's a weird one. 11 times 11 is 121. Most of the 11s are kind of easy to do, but 11 times 11 is a little bit weird. And then we have 12 times 12. 12 times 12 is 144. That also happens to be the total number of answers that we have to put into this 12 times 12 multiplication table. There are 144 answers. We now have filled in an awful lot of them though. And I know that when I was learning my multiplication tables many years ago, I learned 144 actually rather early on because I couldn't help myself as I was doing all these easy ones, the 2s and the 1s and the 3s, etc., the 5s. I couldn't help but look down at that bottom right corner where all the 3-digit numbers were and sort of jump ahead and say, wait, I wonder what it's going to be like when I'm doing those. And of course I couldn't help but notice that one in the bottom right corner. because it's right in the bottom right corner, so you see it. And I thought, oh, 144, well, maybe that's not going to be so hard to memorize because there are 2 4s in a row in it, for one thing. It's kind of interesting. 12 times 12 is equal to 144. And I realized that I actually learned that earlier on than some of the other answers that are smaller numbers. So 144, biggest number in the whole table, if you only go up to 12 times 12. And yet I learned it fairly early on, and it turned out not to be so hard. So we have this nice green diagonal line going across our table. And there's one other thing that's worth saying about that green line. That diagonal line of squares is what I really should call it, because not all of the students are necessarily using green pencils or green pens to fill in that part of the table. So it doesn't have to be green, but the squares, the diagonal line of squares, is very important because you have a sort of a reflection of the part of the table that's down here below and to the left of that line, and the other part of the table that's above and to the right of that line. And we can already see some of that because if we filled in so many of the answers so far, that we see, if we look at that line, it's almost like a mirror, where this 6 has a mirror image on the other side. But look here, the 4, which is further away from that line, has a mirror image for over there. This 12 is right next to, if we look diagonally, we have a 12 and then we have a 15. But over here we have a 15 and a 12. Let's look even further. We have a 7 and then a 12 and then a 15. And here we have a 15 and then a 12 and then a 7. So we see this reflection thing is happening. And the important thing to know about that reflection thing is it makes you realize that that great big table that seemed like so much work is actually only half as much work as you thought. Because if you could do this entire section of the table, including the diagonal line, but everything below and to the left of it, it means you must already know all the answers that go on the other side, because those answers are mirrored on that side. Very important line to learn, that diagonal line. Very important set of numbers to learn. Then, what should we do next? We have to decide what we think might be a nice one to work on. So I'm trying to think like a student who has learned all this stuff and is really feeling quite confident with all this stuff. Some of it's still a little new and they want to practice it some more, but they're feeling like, I know all that, that's great. What should I learn next? I have 2 or 3 opinions that I'm not sure which one to choose. The 3s might be kind of easy to learn next because they involve smaller numbers, and counting up by 3s wouldn't be that unusual a thing to do. That's something we may have already entertained ourselves doing while we were learning to count. Counting up by 3s. So the 3s might be it. 4s might be it too, though. Instead, though, 4s might feel easier than 3s because 4s are they're even numbers. And there's a lot of stuff that involves 4s, things that are grouped into 4s in the real world that makes us feel familiar with numbers in the first place. So maybe it's the 3s, maybe it's the 4s, but I have my opinion. This is green. I want to use another color to show another pattern. I've decided I'm going to jump ahead, and you don't have to. Other students and teachers don't have to do these numbers in the same order as me, but I've decided I want to jump ahead to the 11s. I like the 11s because 11 is a double number, right? 11 is 1, 1. And if we look at what we've already done with the 11s, we have 11, which is 2 1s, and right below it we have 22. 2 times 11 was equal to 22, and 22 is also a double number. And look, 5 times 11 is equal to 55, another double number. So this double number pattern is worth noticing and taking advantage of. I feel like using my orange chalk. So what I'm going to do is I'm going to do all of the 11s now, and I'm going to use orange chalk for all of them, including the ones that we already did before. So I'm erasing that 11 and I'm putting an orange 11. I'm erasing this 22. Oh, I'm erasing a little more than I wanted to there. Orange 22. Fix the little mess that I made with my table there. Okay, I'm going to more carefully erase this 55 and write an orange 55. And then things get a little weird down there, so I'm not going to do those yet. I'm going to do these 11s first. This 11 I'm going to rewrite as an orange 11. And then this 22, I'm going to rewrite as an orange 22. And then this 55, I'm rewriting as an orange 55. Oof. My handwriting gets really messy when I'm down there. Okay. So avoiding this section here with the 11s because they're getting a little different looking. That's an 11. That's an 11, that's an 11. But the 3-digit 11s look a little different. Let's stick with the 2-digit ones and we'll follow the pattern. 11 times 3 is indeed going to be 33. And 11 times 4 is 44. So the double number pattern keeps on working. 11 times 5 we already did. 11 times 6 is equal to 66. 11 times 7 is equal to 77. 11 times 8 is equal to 88. 11 times 9 is equal to 99. And then going down with the 11s, 3 times 11 is equal to 33. 3 times 11, I will remind you, is equal to 11 times 3. 4 times 11 is equal to 44. 5 times 11 is equal to 55. 6 times 11 is equal to 66. 7 times 11 is equal to 77. 8 times 11 is equal to 88. Oh, that 8's messy. That is horrible. 9 times 11 is equal to 99. And then we have no choice but to finish our orange 11s with some non-double numbers. So 11 times, where'd it go? 11 times 10 is equal to 110. And that one's not so bad. Fix this. 110 still has a double number in it. See the 2 1s in a row? But because we're multiplying by 10, we take the 11 and we stick a 0 after it. That's another thing that makes the 10s kind of easy. 10 times 11, so this 10 over here times that 11 is also 110. Let me put that in orange. Now, what about this 121? It's already green for a good reason. Should I erase it and put an orange one? I think not. I'm going to keep the green diagonal line. So all that's left is 11 times 12, which goes here, or 12 times 11, which goes here. And that one's a little bit strange, I admit it. And I remember at that one, it took me a little longer. The 144 came rather early. I talked about that. Even that 121 came rather early. I found the 110s kind of easy. I just had to sort of make myself memorize 11 times 12 is equal to 132. And trying to come up with a way to explain that to make it make sense. The best thing I can think of is, I know that I keep on adding 11s when I count up by 11s, so it has to be a 121 plus 11. And 121 plus 11, we can see how that turns into 132, and it doesn't feel so strange. And then of course we have 12 times 11, this one, which is also 132. So I have used my orange chalk for the 11s, except for that one, where I used the green chalk. And now we're seeing, oh boy, I'm getting pretty close to the end of the hour I planned. I will go over the hour if I have to, because I'd like to at least fill in the rest of the table. But we are getting to the point where there's not very many numbers left, but some of the trickier ones are still there. And those are the ones that students will spend a lot of time on. They will want to spend more time on those ones they find tricky just to get those last few numbers that they haven't memorized yet. Students get to a point where they've memorized all of this and they feel comfortable with all of this. Some of it might still feel a little new, but they're getting there. And then they want to conquer these last little bits of territory. And to me, now I'm going to go back to those 3s and 4s, and I'm switching back to white chalk. 3s, counting up by 3s. 3 times 1 is equal to 3, 3 times 2 is equal to 6, 3 times 3 is equal to 9, 3 times 4 is equal to 12. 3 times 5 is equal to 15, 3 times 6 is equal to 18, 3 times 7 is equal to 21. Sure, I could just count up by 3s, I know I could, and it wouldn't be as many words, and it would make me not need to take sips of my fizzy water as often. But I want to remember that it is multiplication I am working on. 3 times 8 is equal to 24. 3 times 9 is equal to 27. 3 times 10 is equal to 30. 3 times 11 is equal to 33. 3 times 12 is equal to 36. 1 times 3 is 3. 2 times 3 is 6. 3 times 3 is 9. 4 times 3 is 12. 5 times 3 is 15. 6 times 3 is 18. 7 times 3 is 21. 8 times 3 is 24. 9 times 3 is 27. 10 times 3 is 30. 11 times 3 is 33. 12 times 3 is 36. And I have filled in the 3's. If the 3's are not so easy for you, if you're struggling, slow down. Work on the 3's for a while. When it's time to work on the 3's, you work on the 3's. If you have worksheets that are all about multiplying by 3, do those worksheets. Do them twice if you have to. Do lots of multiplying by 3's and you'll start remembering them more and more easily. We did all the 3's, I have to do the 4's. I'm not even going to show all the ones that I already did. I'm going to start with this blank space over here. Realize that for the 4's, I only have 1, 2, 3, 4, and over here 5 empty spaces. For these 4's, I have 1, 2, 3, 4, 5 empty spaces. And it's going to feel really good if we fill those 10 empty spaces, because then look how little there is of the territory we haven't conquered yet. 4 times 1 is 4. 4 times 2 is 8. 4, 8, 12, 16, 20. It's going to be 24, isn't it? Wait, slow down and say it as a multiplication. 4 times 6 is equal to 24. 4 times 7 is equal to 28. Maybe that's a bit of a weird one for some of the students who are just getting to the 4's. 4 times 8 is equal to 32. Maybe that's a bit of a weird one. 4 times 9 is equal to 36. But now we're back into some comfortable territory. 4 times 10 is 44. 4 times 10 is equal to 40. Slow down, Doug. 4 times 11 is equal to 44. 4 times 12 is equal to 48. And now we want to do these. 6 times 4, of course that's 24. 7 times 4, of course that's 28. Taking advantage of that mirror image across the green line. 8 times 4 is equal to 32. 9 times 4 is equal to 36. 10 times 4 we did. 11 times 4 we did. 12 times 4 is equal to 48. And now we're into this, just this little chunk in here and here, and we have those 12s. Which is easier? Should we finish the 12s? Or should we go into those weird little, well, 1, 2, 3, 4, 5, 6 answers, but 1, 2, 3, 4. It's really only 6 answers. We know that whatever goes in here is going to be mirrored over here. It's not so bad. It's only 6 of them. And over here, we only have 4 missing 12s, and these are really the same 4 missing 12s. I might be able to do this in an hour after all anyway. Take-home message is the important thing. At any stage in the learning of the table, it's a good idea for you to fill in all the ones that you think are easy, that you really know, and then take a photo of that table or a photocopy or somehow make a copy of it and print it. Print it, several copies of it. And then you, if that happened right now, if I was a student who was at this phase where I'm really good at all this stuff, and these 6 and these 6, which are the same 6, and these 4 and those 4, if that's what I need to work on, if that's what I have to focus my attention on, I might really want a table that looks just like this, with these empty spaces, and have several copies of it. And then start filling in the empty spaces in the copy. Take another copy, do it again. Focus on those. So counting up by 12s, 12 times 1 is equal to 12. 12 times 2 is equal to 24. If you're familiar with dozens, this isn't really as hard, but I don't know how familiar all the students are with dozens. Dozens of eggs. 12 eggs in a dozen times 6 dozens of eggs. 12 times 6 is equal to 72. Yes, some memorization is necessary. 12 times 7 is equal to 84. 12 times 8 is equal to 96. And then we get to another one of the 3-digit numbers. 12 times 9, that's probably a bit of a weird one for a lot of students. 12 times 9 is equal to 108. But those 4 numbers I just put in also will go here. 6 times 12 is equal to 72. 7 times 12 is equal to 84. 8 times 12 is equal to 96. 9 times 12 this special moment is equal to 108, and I have now done all of the 3-digit numbers. Where are they? Here, 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 here. Here, 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 and oh, so there's 4 and 4, but here there's 3 and there's 3. Yeah, 3. Okay, oh, and then there's that 100, but of course 100 was one of the easy ones, I hope. Okay, now we have those last few. The last few are very often going to be among the ones that students who have learned most of the multiplication tables still occasionally get wrong or have to slow down and think a little bit more in order to get them right. And you don't want that to always be coming back and distracting you when you're trying to do other types of math and focus on new math lessons. So it is worth slowing down and spending a bit of time with these 2 little chunks of numbers, which is really 1 chunk of numbers. So let's get into them. 7 times 6, I know from experience as a teacher, 7 times 6 equals 42 is one of the last numbers a lot of students will learn, one of them. 6 times 7 equals 42. There we have that little mirror image. Okay, we got that one in there. 8 times 6 is equal to 48. But of course 6 times 8 must therefore also be equal to 48. And we look at the pattern again. Let's look at that diagonal pattern. 24, 33, 40, 45, 48, 49, 48. Interesting how the numbers, as we get closer to the green line, get closer together. 48, 49, 48. Okay, so we did 6 times 8 and 8 times 6. How about 6 times 9? 6 times 9 is 54. And in my brain, I'm remembering learning this in the first place and how I still do it now. In my brain, something's happening where I'm saying 6 times 9 is not 45, it's 54. And I know 6 times 9 is not 45 because I do know that 5 times 9 is 45. So the fact that I already learned 5 times 9 helps me to remember 6 times 9. They're close together in the table and taking advantage of the patterns in the table. And I'm remembering partly because 45 and 54, the same 2 digits, but they're in reverse order. Something about 9s. 9s are cool though. 9s have a lot of interesting patterns just on their own. So I did 6 times 9 is equal to 54, so I also want to do 9 times 6 is equal to 54. Nearly there. 3 more answers really to fill in 6 squares. 7 times 8 is equal to 56. 8 times 7 is also equal to 56. Another one to get used to. 7 times 9 is equal to 63. 9 times 7 is equal to 63. I don't know, I never really had that much trouble with the 63. I think the 54 and, oh, this one. You know what? I think we've gotten down to the last answer, the last product in the entire table that I really learned and started to feel comfortable with. It was this one. 8 times 9 is equal to 72. 9 times 8 is equal to 72. You know what? I even had that feeling as I was saying it out loud just now. Wait, am I sure it's 72? Wait, maybe I should go to a calculator and double check or something. Because I had a moment where I was doubting myself, even though I memorized this a very long time ago. 8 times 9 equals 72. 9 times 8 is equal to 72. It was really maybe the very last one of all of these that I learned. Surprisingly, it was not one of the 3-digit ones that I took the longest to learn. It was one of the ones that was kind of lost in this little section of the table. And that's going to be among the same multiplications that are the last to be learned by an awful lot of students. It is worth the trouble to do it though. Do not learn most of these and then say, okay, I think I know enough. I just won't bother learning the last few. I think I've met a few students in my teaching career who seem to have done that. And that sort of thing sort of follows you around and makes you not feel very confident in math. And you want to feel confident with this stuff. We use these so often. Common denominators for adding and subtracting fractions. Oh, We use this so much when we're doing that. And there are plenty of other types of math where we use this stuff a lot. So I have gone almost 5 minutes over the amount of time I meant to spend on this lesson, but that's not so bad. I'm going to say goodbye. I'm going to let the dog say goodbye. She knows that it's nearly over. She's looking at me all like crushed, you know, squished down, all looking comfortable like dogs are so good at, with the tail moving. Because she knows it's supper time. Okay, so I'm going to pick her up. I'm going to say goodbye. She's going to say goodbye. I'm going to fill her little dog dish, all 6 of the little areas, with food. And we're going to see whether she finds all of them tonight. But if she knew her multiplication tables, I bet she would always find all of the food in the dog dish. You have to work on this some more. Okay? Okay? Yeah, I'm getting too close, aren't I? Yeah? Okay, you listening? Okay, thank you very much for being here. I will see you next time for more Math with Doug.